Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video we're going to learn about how to actually calculate how much wood elements are going to shrink due to changes in moisture content. And we're using the approach from the Canadian wood standard, which is 086, in this case edition 086 from 2014. And first I'm just going to explain how to calculate the shrinkage based on the simple equation in the standard, and then I'm going to do a couple simple examples. So how do we calculate shrinkage in 086? Well, it's not a part of the main standard, but there is a section in the appendix to the standard, which is published with the standard, that gives a recommendation for a way that you can calculate wood shrinkage, and that is in Appendix A 5.4.6. So you can refer to that in your wood standard printed copy. So in this, it talks about how we need to pay attention to shrinkage, and it gives some reasons why we should need to take into account shrinkage, including non-uniform movements, metal components that are supporting large timber components, which qualitative example I gave in a previous video about moisture content, and also trying to account for differential movements. Now, a lot of these things, hopefully, we can use the equation to get an idea of how much the shrinkage is going to be, but in order to actually deal with the shrinkage, you're really going to have to rely on good wood structure detailing. So how do we detail the connections, and how do we lay out the elements in order to minimize the problems caused by wood shrinkage? But in order to calculate wood shrinkage, we use this very simple equation. S, which is the amount of shrinkage, is equal to D times Mi minus Mf, which is the change in moisture content. D is the dimension that we're looking at, multiplied by C. Okay, so S is the shrinkage or swelling. This is depending on if you have an increase in moisture content, which will cause swelling, or a decrease in moisture content, which will cause shrinkage or swelling. In the dimension being considered, you'll recall that depending on which dimension you're talking about, whether you're talking about a cross-sectional dimension of a piece of wood or the longitudinal direction of a piece of wood, the shrinkage is different, and it's the C parameter that accounts for that. D is the dimension. So that will be either the width of your piece or the height of your piece cross-section, or the length of your element. And Mi is the minimum of the initial moisture content. So where does your moisture content start? Or the fiber saturation point, which we talked about before. Beyond the fiber saturation point, there is no shrinkage or swelling. So all of these are given in the context of a shrinkage. So Mi is basically the initial, Mf is the final moisture content, but you'd have to flip these in order to consider swelling. So this is final moisture content. Okay, and then the kind of most important part of this, which is how do we know how much it shrinks or swell? We use this shrinkage coefficient, C, and that is equal to a different value depending on whether we're talking about perpendicular to grain or parallel to grain. So they give some categories for lumber, and it says in the standard, if you're using a different kind of wood product, then you'll kind of have to look up either from manufacturer standards or some other way what would be the actual shrinkage coefficient for that product. But if we're talking about regular lumber, then it recommends that C is 0.002 for perpendicular to grain, and 0.0000405 for parallel to grain. So the perpendicular to grain value here is basically my cross-sectional shrinkage, either width or height of the cross-section, because those are the perpendicular to grain directions. And parallel to grain here is the longitudinal direction of the piece of wood. So you can see, you know, about an order of magnitude difference between these two. To the degree that probably in a lot of cases you can ignore the parallel to grain shrinkage and just consider the perpendicular to grain shrinkage, unless you have really long members. And that's really all there is to it. So we just sub these things in. One thing that you need to remember is that MI is given in a percentage, but we don't put the value in as a percentage. So for example, you know, like if I went from 28% to 12%, then what I'm actually going to put in that is going to be, if I can do the, you know, 16. I'm going to actually put the number 16. That's 16%. This is 28%. This is 12%. But I'm not going to put like 0.16. I'm going to put actually 16, because these C values are given in, basically this is shrinkage percentage per percent moisture content difference. Okay, so C is a shrinkage percentage. So 0.002 here is 0.2% shrinkage. So it's 0.2 basically times the length for each percentage change in moisture content. So 16 is the number that I have to put if that was the case for 28 to 12. Okay, now if I had 30 and I went down to 12, if I had 30% here as my initial and then I changed it to 12, my change in moisture content is still going to be 16 for the purposes of this equation. Why? Because between 30% and 28% moisture content, there is no shrinkage, because 30% is past the fiber saturation point. And past fiber saturation point, we don't get shrinkage. So if I went from 100 down to 12, it's still going to be 16% change in moisture content for the purposes of calculating shrinkage, because from 100 down to 28, we don't have any change in dimension size. And then past 28 down to 12, that's when we actually have changed this in dimension size. So let's look at an example. First, starting with a very simple example, which is basically identical to the qualitative example that I gave in the other video about moisture and shrinkage, where we have this girder and a joist, and the joist is going to shrink up towards the bolt because the bolt is restraining it from moving. So this is a bad design. We would really want the bolt to be down here if we could, because then only this dimension will be involved in the shrinkage. But that's not what we have. So we have to do this calculation to see if this is going to be a problem or not. So when this joist was installed, the moisture content was 19%. During service, we're expecting it to drop as low as 5%. So we have a pretty dry interior area. So after some time, if I have a dry area, the equilibrium moisture content of the piece of wood is going to go down to 5%. These are just example numbers. You know, where is there a gap going to be forming, and how wide will that gap be? And we know that from the previous video that what's going to happen is this is where my joist is restrained, and this is going to shrink upwards from here, and it's going to shrink downwards towards here. Okay, because that's the level at which the joist is restrained, so it's going to shrink towards the restraint. So basically the gap is going to form right here, right? And we want to know how much it's going to, how much of a gap we're going to get. Okay, so it's pretty easy to calculate. Yeah, let's keep that. So I have, again, S equals, right, D times MI minus MF, all that times C. So C is my coefficient of shrinkage, my shrinkage coefficient. D is the dimension that we're looking to calculate. How much is that dimension going to shrink? And MI minus MF is my change in moisture content. So, you know, it's going to start at 19. So let's do the dimension first. So S equals, the dimension that's going to shrink here is 220, because it's going to shrink. The 220 dimension up top is what's going to shrink up, okay, to form the gap. MI is 19. MF is 5, okay, because we're going from 19 moisture content to 5% moisture content, but I'm just leave the percents off. And C in this case, because we're talking about shrinkage perpendicular to grain, okay, shrinkage parallel to grain would be this direction, right? This is the grain direction. Okay, so any other direction is perpendicular to that grain direction. So basically, as a rule of thumb, as long as I can figure out what's my longitudinal direction, which is also my grain direction, any other dimension is perpendicular to grain. So up here is perpendicular to grain. Out of plane for this joist would also be perpendicular to grain shrinkage. And so since we're talking about perpendicular to grain, my C is 0.002, and don't forget that this is in millimeters. This 220 is in millimeters. Okay, and 0.002 is percent per percent, basically. And 19 minus 5 is also percent. So these don't have actually units associated with them. So S is going to equal 6 millimeters if I calculate that out. Okay, and that's my final answer. So basically what's going to be left here at the gap is going to be a 6 millimeter gap. So if that can be accommodated by construction tolerances and holes around the bolts and stuff like that, then we're going to be fine. But if it doesn't, then we might be in trouble. And it also depends on kind of how stiff the wood connection is at the bolt. Now, bolt sizes are typically only about 2 millimeters bigger than the bolt. So we might have 2 millimeters of space to play with to accommodate that kind of shrinkage, but 6 millimeters is probably going to be too much. So this connection is probably going to have a problem. So we should redesign this connection basically to move the bolt down to somewhere lower. Okay, looking at a second example. Here we have a light frame shear wall, okay, which we talked about in the kind of examples on what wood structures look like. So this shear wall is 8 feet tall, 8 feet, which is a typical size for a shear wall. Why is that? Because plywood comes in 4 foot widths. They're basically 4 by 8. So that means you don't have to cut your plywood. So we have not the sheathing, the plywood sheathing or the OSB sheathing is not shown here, but we have studs, which are the vertical members. These are the studs, right? This is a bottom plate, right? There's a top plate, top plates. There's 2 of them there. Okay, and we want to know how much this light frame shear wall is going to expand vertically if the moisture content increases from 5% to 100%. So let's say wherever this is, it happened to get really wet. So maybe I had a failure of my rain screen or something outside, like the envelope has failed and the wall has been, you know, has had a lot of water come in, and all these, the moisture content's gone up to 100%. So what's going to happen is what I want to know. What is going to be the vertical swelling? So since we're going from a low moisture content to a high moisture content, now we're going to have swelling. So everything's going to get bigger, and we want to know by how much. And it says all the members here are 2 by 6. 2 by 6 means nominally 2 inches by 6 inches, but as we discussed in the moisture video as well, it's not actually 2 by 6. It's more like 1.5 by 5.5 or something like that. So it's 38 by 140. Those are the millimeter direct dimensions. So I've given those to you. We will have to convert the feet into something metric so that we can deal with these. So let's get started. Okay, so we have horizontal members and we have vertical members. Okay, so we have these orange ones. This is horizontal, horizontal, and horizontal. So we've got 3 different members that are horizontal, and we've got 1 member basically which is vertical. So if I'm looking at a vertical line, I have horizontal, horizontal, vertical, and horizontal. Okay, so I have 3 horizontal members and 1 vertical member along the height of this wall. Okay, so I want to figure out how much each of these layers is going to expand. all the horizontal layers are the same width, so I'm just going to make that calculation once, and then I can multiply it by 3. And for the vertical one, I'm going to have to figure out what the height of that is, and then how much the elongation is for that stud. Okay, so if I'm looking at the horizontal members, first, okay, which are 2 by 6, 38 by 140, which we know from above. Okay, I have S is my shrinkage, D, MI minus MF from the appendix to the standard multiplied by C. So in this case, D is equal to 38 millimeters. These studs, you have to understand a bit how these walls are put together. The studs are laid on the flat. So each of these here, this dimension is 38. The 140 is out of the page. Okay, so these are laid on the flat. Just like the vertical studs are also 140 out of the page, and the width of them is 38. Okay, so I'm looking for the vertical dimension along this height. So if I'm talking about the horizontal member, I have the horizontal member lying flat like this. Okay, so it's lying flat like this. It's 38 in this dimension, 140 in the out of plane dimension. So the dimension I'm interested in is the 38, which is the thickness of that. That's the dimension that's going to expand or contract. In this case, expand. Okay, so if that's 38, then I can, and C in this case is going to be 0.002 because we're perpendicular to grain. Perp for short, perp to grain. Okay, because I'm expanding a width or a height of the cross section, not the longitudinal length of the section. Okay, so therefore, what's my S? Is equal to 38, which is my dimension. And then I have MI minus MF. Okay, in this case, my MI is going to be 5. I start at 5, right? So that's my moisture content that I start at. And then I go to 100, right? But I'm not going to put 100 here because past the fiber saturation point, there is going to be no swelling, right? So I can only swell up to the fiber saturation point, which is 28, and no further. So I don't put 100 here. And then C is 0.002. So if I calculate that out, I'm going to get negative 1.75 millimeters because the D was 38, was in millimeters. If that D was in inches and I did this calculation, it would still work. I would just get a number out in inches. So here the negative is just an indication that this is swelling. But I wouldn't get too caught up about the pluses or minus. The best thing for you is to understand what's happening so that you know that this is swelling, because we've seen that we're going from low moisture content to high moisture content. I could have just as easily put 28 minus 5 and said it's swelling, because I know that it's swelling. Okay, so that's how much each horizontal member, so this is each horizontal member is going to swell by 1.75 millimeters. Now, what about the vertical member? Vertical member, which is also a 2 by 6, right? 38 by 140. Okay, but in this case, we need to know the height of the member because we're looking to calculate the elongation in the vertical direction. Okay, so we need to know this. That's not the best place to put it. We need to know this height here. This height, that's the length of the vertical member, right? Of the vertical member. So how do we find that? The total height is 8 feet. Then we subtract 38 and 38 at the top and another 38 at the bottom. And that's how we're going to get the total length of our member, right? So just to remind ourselves about how we convert feet to millimeters, right? We got 12 inches in a foot, and each inch is 25.4 millimeters. That's something that you really have to put to memory because, especially in wood construction, we sometimes run into things that are in inches instead of in millimeters, and we need to know how to convert them. So, but the only thing that you really need to remember is 25.4 millimeters. So just remember 25.4 millimeters per inch, and you're gonna be just fine. So what's the height of this member? Okay, it's 8 feet, right? Minus 3 times 38 millimeters. So let's get all those into the same units. So we have 8 feet times 12 inches per foot times 25.4 millimeters per inch. All right, minus 3 times 38. Then if I calculate that all out, I get that the height is 23.24 millimeters. Okay, so now that I know the height of the member, I can calculate the shrinkage as long as I use the right coefficient. Now the coefficient that I'm going to use in this case, since it's longitudinal shrinkage, it's the member that is shrinking along its own length. So it's in the grain direction, the parallel to grain direction. I'm going to use 0.12340 because that's the parallel to grain shrinkage coefficient. Parallel to grain. And if I do that calculation, I'm going to have 2324, which is my D, 5 minus 28 again, and 0.00005. And what I get is 2.67. I can put a negative on there, millimeters, which is swelling. Okay, so you can see that the shrinkage for the top plates and the bottom plate is 1.75 millimeters each, even though they're just, you know, 1.5 inches. And the shrinkage of the vertical member, which is much, much longer, over 2 meters long, is only 2 millimeters, 2.7 millimeters. So if I want to now find the final total swelling, we're going to have S total is going to equal 3 times S of the horizontal members plus S of the vertical members, and we get 3 times 1.75 plus 2.67, and all those are in millimeters, and we get 7.92 millimeters, okay, which is equal to about 8 millimeters of swelling. So that's my final answer. Now, is there any point to saying 7.92 millimeters? If you do this on a test or an exam, or if you're doing it for your boss and you're working as an engineer and you go to your boss and you say, okay, I've calculated this swelling and it's going to be 7.92 millimeters, then everybody's going to laugh at you, right? Because there's no way that we know the swelling to that accuracy. Okay, I think in terms of shrinkage like this, probably 1 sig fig is probably enough, because remember, the actual shrinkage coefficients, we have the difference between we have the difference between radial and tangential shrinkage, which is a difference like we saw in the moisture content video, and we don't know which direction it is or what combination of directions. It depends on how the lumber was sawn from the log, like in which direction, is it quarter sawn or whatever. And in addition to that, the actual shrinkage coefficients are also very rough numbers. You'll see the shrinkage coefficients 0.002 and 0.00005 each only have one significant figure because we don't know them that well. They're only approximations. So that's all there is to basically know about shrinkage for the purposes of this course, and we're going to follow up with another example in the live session that we can do together.